We'll get started in just a second. All right, everyone doing okay? Yeah. Okay, so we are going to continue with what we left off with. I put you in groups, and I had asked you to try and determine whether or not we had a right triangle given the three vertices of a triangle. So now we're going to continue to the next topic in this section. We're still in the dot product section. So we're now going to be talking about two different concepts. The first concept here is called vector projections. So this is going to actually come up very, very helpful later on as we move through this chapter. So given two vectors, we can project one vector onto the other. And we like to look at it as like casting a shadow. So I have a two-dimensional example here. So right now, let me switch this. Just focus your attention on the red vector and the blue vector. And notice I have them attached tail to tail, right? So, you know, this blue vector could really be anywhere, but I'm going to move it to where it's connected to the red one. And then what we're going to do is project the blue one onto the red one. So you're casting a shadow. It's almost like you had a light source and you're casting a shadow onto the red vector. And so that shadow should create a new vector that's projected onto the red vector. And it is like, we call this like a perpendicular projection. Okay, it's like we're dropping a line that's perpendicular to the red one from the tip of the blue one. And then you create this purple vector called the vector projection. Now, if I change the length of the red vector, nothing changes in terms of the vector projection, okay? In fact, even if I make the red vector shorter than the purple one, the vector projection is still going to be this purple one. So whenever you have a vector that you're projecting onto, you can almost imagine it like a straight line, and you're just dropping a perpendicular down to that line and then creating a new vector. And I can even point it in the opposite direction. And even if that vector is in the opposite direction, the vector projection will still be this purple vector. Does that make sense? Are there any questions on that? Now, what we're looking at right now is the projection of the blue vector onto the red vector. You could do it the other way. You could project the red one onto the blue one. So I'm just going to put these here. Let me show you the change. I'm about to project the red one onto the blue one. So imagine now, since the blue one's the one we're projecting onto, I'm going to just extend the blue vector in both directions. I'm going to go to the tip of the red one, and I'm going to drop a perpendicular line down to the blue, the blue vector's line, right? And that is where my projection vector is. Okay, so all I have to do here is switch it and you'll see it. So now I'm going to go red onto blue. Yeah, close enough. Okay. I'm going to move the red one around. You'll see here, if I move it to the other side, the vector projection is now this vector. Okay. Any questions on that? So we need a formula, right? If I give you two vectors, we need a formula that will allow you to find this new vector. And here's the vector projection formula. So this is the notation we use. Whenever we want to do a vector projection, we write PROJ for projection. And then you subscript it with V, and then you just put the U vector here. So I like to look at it, since the V is on the bottom here, I always think of it as we are projecting this one onto that one. Okay, so U is going on to the one on the bottom. So the formula for this vector projection of U onto V is equal to this. So you're going to take the dot product of the two vectors, and then you will divide it by the length of V squared. So you take the two dot products, or the dot product of the two vectors, and then you look at the vector you're projecting onto, V, find its length and square it. Now, everything that you see here, is a number. Think about that. V dot U, that's a dot product. The dot product to two vectors is a number, right? And then you take the magnitude of V, that's how long V is, that's a number. You square it, that's a number. And so you're taking a number divided by a number, so this should just be a number. So this right here is, what we're saying is that we're going to be taking some number and multiplying it times V, which means that the projection vector should be a scalar multiple of V, which means it should be parallel to V. And that's what we see in the picture, right? So if we are, let's just say for the sake of demonstration, this is the vector V, the blue one, and this is U, then I'm projecting U onto V. Notice that the purple vector is a scalar multiple of the blue vector, right? And that's what the formula should indicate, which it does. Okay, now, if you change this around, right, what would happen if you change it? What if you wanted to do the projection of this time V onto U? This time you would do U dot V over the magnitude of the vector you're projecting on, squared, and then times U. So again, you'll have a scalar multiple of U here. So some scalar in front of U. All right. So sometimes when we do a vector projection, or when we do a vector projection, our answer is a vector. Sometimes we just want to know the length of that vector, just how long it is, okay? So there's a different formula to get you the length of the projection vector. Now we have a different name for it. It's called the scalar projection, or sometimes it's called the component of U onto V. So instead of the projection of U onto V, we call it the component of U onto V. And the notation is comp, and then the same thing, U onto V here. And the formula is just the dot product of V and U divided by the length of V. So it's a simpler formula than the previous one. And notice that this answer is just going to be a number, right? You have a number on top. The length of V is a number. So a number divided by a number should be a number. And that number is going to give you the length of the projection vector. Okay, so those are two different things. Go back to our picture. One thing I could ask is, what is this purple vector? That would be the projection. Or I could say, how long is that purple vector? That would be the component. Any questions? We're going to do an example, but are there any questions? All right. So this is just to illustrate that. Let me switch it. If I project this blue one onto this red one, I'm having the computer do this for me. It's giving me the projection vector. Now, please understand that my computer did not want to do angle brackets. This is supposed to be angle brackets here. And so this is the actual vector. This purple vector is this vector. So the computer is doing the projection formula there. And then I have the computer doing the component formula, and it's spitting out 3.5. So the vector is, in this case, 2.9, 1.9, right? But its length is 3.5. All right, so our turn. find the projection of u onto v, find the component of u onto v, given these two vectors. So let's start with the first one. Let's do the projection. You know what I'm gonna do? I'm gonna copy this. This is very just computational. There's no magic happening here. There's no real deep thinking. Okay, we just need to be able to apply the two formulas. So why don't we just jot down the formulas here? Projection, oops. Projection of u onto v should be v dot u over the magnitude of v squared times the vector v. And then component of u onto v should be what? Is it similar to that formula? The component? What are the similarities?
You just don't multiply by the vector at the end.
And we don't square the bottom.
Yes.
Okay, and we don't square the bottom. So it's just going to be that same thing, v dot u over the magnitude of v, like that. All right, so would you all agree that we need to find the dot product, right? We're going to need that for both of the answers. So let's go ahead and do v dot u. That means we're going to take the vector v, negative 3, 7, and dot it with the vector 2, 4. And if we do that, then we get what? Negative 6. We multiply these two, right? Negative 6 plus 28 should be 22. So that's v dot u. And then we also need the length of v in both of these. So the length of v is the square root of the sum of the squares of the components. So that's square root of 9 plus 49, which equals the square root of 58. And now we should be able to spit both these out, right? So let's do the projection first. Projection of u onto v should be equal to, okay, so first it's v dot u, which we said is 22, over the length of v, but squared, right? So when you take the length of v, which is root 58, and square it, that should just give us 58. But then times the vector v. So what I'm going to do is I'm going to write my vector, negative 3, 7. And this is scalar multiplication, which just means we pass the 22 over 58 through the angled brackets, almost like distribution. And our answer is still a vector. So when I multiply this through, we get what? Negative 66 over 58. And then what's 22 times 7? 154? Someone can check my arithmetic. 154 over 58. Y'all agree?
Isn't it just the v vector that you multiply by?
What the what?
Isn't it just the v vector that you multiply by? So it's like negative 3, 7, not 6 and 28.
I'm not sure I follow you. 6 and 28. What do you?
Oh, never mind.
Sure. You're good?
Yeah, I saw what I did wrong.
Okay. Okay. So this is a new vector, right? This is a new vector. It should be parallel to v. So it should be, you know, in the same, well, parallel, it's a scalar multiple. It could be in the same direction, could be opposite direction. But this is the vector we should get if we were to project this vector u onto this one. So it's that, drop that perpendicular line, create this new vector. Now, the next thing we need to do is find the component of u onto v. So we just do this, right? V dot, so the component, I'll do it right here so we can see the formula. The component of u onto v should just be v dot u, which is 22 again, over the magnitude of v, which is square root of 58. And that's it. Of course, we could get that as a decimal if we wanted to and figure out, you know, like if we want to know about how big that is. But the exact answer is this. Okay, is that pretty straightforward? Just got to make sure you have the formula. By the way, if I would have accidentally on the top done u dot v instead of v dot u, would it have changed things? No, dot product is commutative. You can always flip it. Now, you don't want to get to the habit of just making that mistake, but it wouldn't have caused any problems. All right.
Mr. Giovanni?
Yes.
And on an exam or a mini exam, did you want us to rationalize or just keep the square rooted
That's
at
a
the
great
bottom?
question. So I'm going to have to go off on a tangent here a little bit to answer your question. Does everyone understand what Jorge's asking? He's saying, is this an acceptable answer, right? Or do you have to rationalize the answer? And what he means is, do you need to multiply the top and bottom by root 58? And to do that, let's see, we'll get 22 root 58 over 58. So that's now rationalized, right? So let's take a poll. Let's see if my poll works here. I don't know why it doesn't save my polls. It used to. I'm just curious. I want to see what y'all think here. All right, here we go. So my question to you, and if you can't get to a poll, if you're on your phone or something, don't worry about it. My question to you is, do we have to rationalize this? Are you allowed to leave square roots in the denominator? Yes or no? So I guess my question is this answer over here okay? Yes or no? Let me pose it that way. Is this answer okay? Yes or no? That's almost all of you have voted. Okay, that's good. We got a couple more votes. All right, so let me share the results. So it's about almost 50-50. About half of you say that that answer is fine just the way it is. And the other half of you are saying, no, we have to rationalize it. So I'd like to hear an argument from the no's first. Anyone who said, no, we have to rationalize it, I'd like to hear your kind of argument to support that. No?
Isn't it whenever you put it into the calculator, it gives you an error?
No, we should be able to type this into our calculator. 22 over the square root of 58. We should be able to type that in, no problem.
I just said no because my teachers in the past have counted it wrong.
Yeah.
So if it is okay, then what have I been doing this whole time?
Yeah, okay. So how about someone who said, yes, the answer is okay? You want to explain or tell me why you think that?
To me, by leaving it there, you don't lose any accuracy in your answer, but you might introduce an error by going in and rationalizing it.
Yeah, so you get the same answer. Okay, so if you type this into your calculator, you can get the same decimal that you would get if you type this into your calculator. But at least half of you have been told that you can't leave it this way. And that's a shame, because there is no difference in the answer. And most people are taught that because the person teaching them was taught that. But there's actually a reason why rationalizing was important. It's not important. It's not important like it used to be. And I'm going to explain it to you. So because this bothered me too as a student. I couldn't understand why you get the same answer either way. Like, why can't I leave a square root in the denominator, right? So here's the explanation. Take yourself back to the days before calculators, right? So before calculators, people doing math had to memorize certain special numbers. For example, pi. They would have to memorize, that this is approximately 3.1415. And you know, maybe you would memorize it out 10 digits. Maybe you'd memorize it 50 digits. They used to have like competitions, you know, like you're in high school, it's like, man, I know pi out 100 digits, you know, that was like the cool thing if you were like a math dork, right? And then there's things like square root of 2, very important. That comes up a lot. That's a 1.414, right? E, which is approximately 2.718. Okay, so before calculators, you had to have these kind of memorized. Now, let's say you're doing a problem and you get to this point, 1 over the square root of 2. Now, you don't have a calculator, but you want a decimal approximation of this. So the only thing you can do is say, okay, well, this should be about 1 divided by 1.414. Yes? Because you've memorized 1.414. Now, to do this division, you have to go back to grade school. You have a division box, and inside the division box, you're going to put 1.000, and on the outside, 1.414. And now you have to start playing this game where you're like, what do I multiply 1.414 by to get 1? Well, I can't. So what do I multiply 1.414 by to get 10? I don't know. I'm not sure, right? It's a little tough. Okay, now rationalize it first. This is what rationalizing would be, right? So now you would get this, root 2 on top, and on the bottom you have 2, right? So now you know root 2 is about 1.414, and now divided by 2, but watch how it changes now. Inside the division box is the 1.414, and outside the division box is a nice number, 2. And so you go, 2 doesn't go into 1, but 2 goes into 14 how many times? 7. So you do a 0.7, then you put 14 here, and then you subtract, you'll get 1, 4. And so 2 doesn't go into 1, but it goes into 14 7 times. So you get 0.707. So you see that that arithmetic is easier to do than the one above it. That's why. That's why back in the day, you always wanted to rationalize your answers so that you could do the next step. But somehow it just stuck. And after computers came along, we still were telling people you have to rationalize, you have to rationalize. Even to today, 2021, we're still sitting here, and I'm sure there's a college algebra class being taught right now where someone's going to get points taken off, but it doesn't make a difference at the end of the day. So it really irritates me. So I'm glad you asked that question. This is fully acceptable to me. Now, if you want to rationalize it, go ahead, but I will take this as an answer. All right, good question. Next thing. So this is the same problem, okay? It's hard to see, but it's the same problem, but this time it's the projection of V onto U instead, right? So the formula changes, right? The formula is going to change. Should we do it? I guess we can. And let me see, I'll leave this one here and I'll do it on new page. Doesn't that bother you? It bothered me for a long time. Still bothers me. Rationalizing. It bothers me when people are like, no, you have to. I'm like, I don't have to. All right, here we go. So the only difference here is that the formula is now going to be projection. Let's see, we're going to go V onto U. So we're going to go U dot V over what? This time it's what?
V.
Magnitude of U.
Right.
Magnitude
Squared.
of U squared. And then times what vector?
U.
U instead of V, okay? So it's just everything changes roles. Now, we cannot use what we did before. Actually, we can do this. We know U dot V is still 22. You all agree with that? It doesn't matter which way we do it, V dot U or U dot V. But we need the length of U, and we didn't do that last time. So the length of U should be the square root of, let's see, 2 squared plus 4 squared. So this should be the square root of 4 and 16, what? 4 and 16, 20, root 20? We good? Okay, so this should be u dot v, which is 22 over the magnitude of u, which is this, squared, which gives me 20, and then times the vector 2, 4. And then we can reduce it. Let's reduce it. So this is 11 over 10. And let's pass that through. You don't have to reduce, but 22 over 10, and then 44 over 10. And yeah, that's fine, but you could go 11 fifths, 22 fifths, something like that. Okay. And then we also need to find the component. Now there's a formula for component, right? There was a formula for component, but do y'all realize, I mean, the formula is easy, all right? I mean, like you could just use it. Component, what are we doing? U here, V here. It's probably easier just do this. But do y'all realize y'all could also just find the magnitude of that vector? Like in other words, you could just say, what's the magnitude of that? Well, that would just be the square root of 11 over 5 squared plus 22 over 5 squared, and then do that and get your answer the same way. I think that's a little bit kind of, I don't know, I'm not gonna say more difficult math, but I think it is a little bit harder. The numbers are a little bigger here than if you just use the formula. All right, can I move on? All right, so look at this one. U is a vector. Now we're in 3-dimensional space, and I should state that everything I've done so far is in 2-dimensional space, but everything extends into 3-dimensional space. The formulas still apply because we can do dot products of vectors in 3-dimensional space. We can find lengths of vectors in 3-dimensional space. Everything just kind of transfers over. So here we're given a vector u is 4, 0, -1. We want to find a vector v such that when you project u onto v, you get a vector that has a length of 3. That's what that's saying. So it's like they're giving you a vector u. Oh, I can't. I'm gonna try and draw this first because I think it's good to understand this before we actually just start grinding away. All right. So we're given a vector in 3-dimensional space, right? Here it is. So I'm just going to draw that vector. There it is. That's the vector u. It's the vector 4, 0, -1. All right, it's in 3-dimensional space. So if you want, you can just imagine. Here we go. You know, there it is, a little Sharpie. Just a vector sitting in 3-dimensional space, right? Pointing somewhere. What you're trying to find is a vector v that when you project u onto the v, so let me just draw a v. When you project that u onto the v, the projection vector, this vector, you want the length of that vector to be 3. Now, I always like to ask my classes at this point, if anybody can, you know, see a little bit, maybe you can visualize 3-dimensional space. Like, what's our answer going to look like? Because we're looking for a vector v that satisfies this, right? Can anyone visualize what v has to be, or is there only one answer? I mean, think about this vector. Project u onto that one. Is it possible that this projection vector could also be 3?
Right.
Yeah.
Are there more?
Is there infinite answers?
Maybe, yeah, it looks like there might be. In fact, imagine they're like a cone. You see a cone around this? Any vector that would lie in this cone, this three-dimensional cone, if you project, right, onto any vector, you would get a projection vector with length of 3. So any vector that passes through this kind of ring would satisfy this. Now that I'm not expecting that you would understand that like first time through, but I'm just trying to get you to see that there is a visual part of this, that it's not just a mechanical problem. This is a visual problem also. Okay, so let's get down to the mechanics. We want the component, of u onto v to be equal to 3. Now, we do know what u is, right? We do know what u is. The formula for that is what? V dot u over what?
Magnitude of u.
Magnitude of
v squared.
v, careful.
Oh, the magnitude of the absolute
No squared.
magnitude of v.
No squared, right? This is a length. So let me just go back to this. Here we go. The component of u onto v is v dot u over the magnitude of v. Okay, that's what we're using. So do you all agree that that must equal 3? Right? Okay, now we know what u is, but we don't know what v is, right? We don't know what v is. So we need to kind of identify v with the vector, three-dimensional. I don't know what it is, so I'm going to call this v1, v2, and v3. So I'm just kind of putting in variables for the components, right? The first component of v, the second component of v, the third component of v. And now you can kind of tell me what the dot product is now. If I tell you to dot these two together, you're going to do v1 times 4, right? So let me write this down. V dot u will be v1, v2, v3 dotted with the vector 4, 0, 1, sorry, -1. And if we do that dot product, we should get a number. Sorry, that's a mistake. 4v1 minus v3. So 4 times v1, and then v2 times 0 is gone. V1 times v3 times -1 is negative v3. Everyone good? That's a dot product. Okay, now we also need the magnitude of v. The magnitude of v, well, unfortunately, we don't know what v is, so this is just v1 squared plus v2 squared plus v3 squared, right? So let's go back up here to our formula and let's fill in the pieces that we found. We found this and we found that, so we should be able to rewrite that. And I'm going to do it right over here so that I can keep it on the screen here. We know that v dot u, which is 4v1 minus v3, over the magnitude of v, which is the square root of v1 squared plus v2 squared plus v3 squared, must be equal to 3. Now, right away, you should notice that we have a single equation, right? We have a single equation, and we have 3 unknown variables, right? And anytime you have one equation and 3 variables, there is not a unique answer. That means you're going to have infinitely many answers. Okay, so because we have infinitely many answers, and the question just said, find v. So that means find any v. That means we can come up with any v we want as long as it satisfies this equation. So what I'm going to do is I'm going to start to fix some of these variables. I'm going to choose them to reduce this down to a single equation with a single unknown. Single equation, single unknown. So I'm going to be smart about this. I think I'm going to be smart. I'm going to try let me try and let v2 be 0. Okay, so remember my vector V is the vector V1. I don't know what V1 is, but V2, I'm going to let it be 0 and then leave V3 alone. I'm going to see if I can't figure out what V1 and V3 would have to be if V2 was 0. So do y'all see I'm just kind of plugging something in? I could have plugged in 1. I could have plugged in any number I want, but I'm going to go with 0 and see what happens. So what happens to this equation if I let V2 be 0? Well, it becomes 4V1 minus V3 over square root of V1 squared. There's no V2, V3 squared equals 3. All right, well, I still have one equation with two unknowns, right? So I need to fix something for either V1 or V2, try and lock something in. So anyone have a suggestion? I mean, we could do 0 again, couldn't we? Could we do 0 again? We could try it. Do y'all want to let V3 be 0?
Yes.
See, okay, now we might run into a roadblock, but let's just see what happens. If we let V3 be 0, I should have put here let V3 be 0. If we let V3 be 0, let's see what happens. We're going to get 4V1 over square root of V1 squared equals 3. Uh-oh, we have a problem. Does anyone see the problem? What's the denominator?
Just V1.
That's just V1. So if you have 4V1 over V1 equals 3, the V1s cancel, and what do you have?
4 equals
4
3.
equals
4
3.
equals 3, not going to work, right? So that means we can't let V3 be 0 or else it's not going to work. So we need to try something else. So how about we let V3 be, I don't know, 1? 1 seems like a decent number to work with. So 4V1 minus V3 is going to be 1 over square root of V1 squared plus 1. That must be 3. I'm hoping this works. All right, so now we need to solve this. So here's what I'm going to do to solve this. I'm going to multiply both sides by the denominator. In other words, I'm going to clear the fraction. Just multiply both sides by the denominator. Now we have a square root equation. I'm going to square both sides of the equation. All right, so you square the left side, you square the right side. And now I have to actually square this thing out. Like I have to square the left and distribute a 9 through. Just stop me if you have any questions. What do we have here? What type of equation is that?
Polynomial.
Polynomial? In particular, what type of polynomial equation? What degree?
Degree 2.
Quadratic.
Quadratic. This is a quadratic equation. We can solve quadratic equations, right? Quadratic formula. So let's get everything over to one side. So I'm going to subtract 9v1 squared. Subtract 9. So let's see what we get here. Subtract 9v1 squared. Subtract 9. So I think we're going to get 7v1 squared minus 8v1 minus 8 equals 0. Which basically looks like this. I mean, this is essentially what we have. You're just thinking more of like a college algebra mind. It's just a quadratic equation, right? It's just our variables v1 instead. So I can use a quadratic formula to solve this. My solutions will be v1 equals, now I'm using quadratic formula, which I'm sure you all know, negative b plus or minus square root b squared minus 4ac all over 2a, right? You've all been through that, done that. So negative b for us will be 8 plus or minus the square root of b squared, that's negative 8 squared, that's 64, minus 4 times a, which is 7, times c, which is negative 8, all over 2 times 7. I'm just going to get on my calculator and crank an answer out here real quick. So 64 plus 4 times 7 times 8. So I'm getting 8 plus or minus square root of 288 over 14. There we go. Now we do have one issue. Do you remember this step right here, where I squared both sides of the equation? We're allowed to do that, right? In algebra, we learned that we're allowed to do that. But what must we do anytime we square both sides of an equation? What must we do with these answers? We have to check them. Okay, anytime you square both sides of an equation, you introduce the possibility of extraneous solutions. That means solutions that don't work. And so we would have to check to see whether or not these worked in here. So I would have to replace this V1 with this and see if it works out. Now, I'm going to go ahead and get this as a decimal. I'm going to get the two answers as a decimal, just so we have them. So one of these answers is 1.78. I'm rounding. The other one is negative 0.641, something like that. And I'll say this one's 784. Okay, these are my two values that I have for V1. Potentially, I'm not sure if these are good. So the way I could check it is I could plug 1.784 in here, square it, add 1, take the square root, multiply times 3, and make sure I get the same thing here. Make sure it's equal. And if I'm not mistaken, I don't think they both work. This one doesn't work. Because if you plug this in, this is a negative number. If I do 4 times a negative number, I get a negative number. I take away 1, I get negative. So I know if I plug this one in, I'm going to get a negative over here, but it's impossible to get a negative on the right side because there's no way to take the square root of something and get negative. So I can chunk this one. So final answer. We had to find a V where when you project U onto that V, the length of that projection is 3. So the V that we found, and this is not the only V, but a V, is, I'm going to go with the exact form, 8 plus root 288 over 14, comma, we let V2 be 0, didn't we? And we let V3 be 1. So there it is. That vector, if you project U onto that vector, the length of that projection should be 3. Any questions? Yes.
So well, I guess theoretically, each one of us can get a different V vector.
Yep, absolutely.
And, okay,
Yes.
okay.
Uh-huh. Everybody could, because I chose V2 to be 0 here to start. You could have chosen V3 to be 0. And then you could have tried something for V1. It's really, everyone has flexibility here. Makes it difficult for me to grade because I have to check each one of yours to make sure it works, but you know, yeah. Okay, moving along. That's it. Okay, so we're done with that section. Don't worry about this homework assignment. It's on your schedule, so just ignore that. So we're done with 10.3, which is dot product. We're ready to start 10.4. And 10.4 is the cross product. So remember I said that there are two types of vector multiplication, right? You have two vectors, right? Two vectors given. You can do their dot product, which gives you a number. And that number has some relationship with the angle between the two vectors. And then you have the cross product. So I know a lot of you have seen cross product if you've done physics or anything like that. So before we can begin, I'll just remind you of the vector notation we had, where you can write vectors two different ways. You could write it the way I like to write them, angled brackets like that, or you could just put that component U1 in front of I hat plus U2 in front of J hat. Those two vectors are equivalent. Okay, so it's just a notation thing there. And in three-dimensional space, if you're given the vector in the bracket form, here's what it looks like converted over to the IJK. Just remember that. Now, we know that dot products give us a number. We know we can take the dot product between any two vectors. Now, cross product, there is a catch. Okay, with cross products, we can only do cross products of vectors that are three-dimensional vectors. So if you have two-dimensional vectors, you cannot do a cross product. Right, so it's only defined for R3 when we're in three-dimensional space. Now, later on, we'll see that there's workaround. There's a way to get around it, okay? So, but for now, for the beginning, let's just say it's only defined in R3. So here's the cross product. We take two vectors, and then the notation we use is this little, it's almost like a multiplication symbol. It's like a little cross, right? In between the vectors. That's how you distinguish it from the dot product. And then there's a formula for it, which you're free to memorize the formula. Okay, but I don't recommend you memorize the formula because there's another way that we can do cross products that's a little more systematic and I think user-friendly. Okay, so just know this formula exists. Memorize it if you want. Instead, what we're going to do is use something like this, and it's just a way to do cross products by hand. And so I'm going to do an example. I think once you see it, if you've never seen it, once you see it, you'll be like, okay, I kind of get it. So I'm going to just do this example. So let's say we have two three-dimensional vectors. Here they are. I want to take this over to my notes. You know, I'm using like so many different programs right now. One of the programs I have, I can just write on the screen, right? And I can do different things. Problem is that doesn't save. Unless you rewatch the video, you won't be able to see that. So I'm trying to go and take these problems and put them into my OneNote program so that when I can save this and post that for you all. But I didn't do that the last few classes, so I'm trying to do that a little more now. Okay, so we want to find the cross product between these two vectors, u and v. So here's what we do. We're going to write down I, J, K, I, J, K. And if you want, you can make little hats. It doesn't matter. I just put I, J, K. Oh, wait a minute. Hold on. Hold on. Hold on. I'm showing you a different way. Hold on. Bloop, bloop, bloop. Take that away. I apologize. We only want to use, I'm doing a different one. I, J, K, just I, J, K. Sorry. All right, so underneath it, what I'm going to do is I'm going to put the two vectors, and I have to put them in the right order. So I'm doing U crossed with V. So I'm going to write the U vector below this. I'm going to leave myself a little space. And then below that, I'm going to put the V. Okay. Everyone understand? IJK, the first vector U, the second vector V. Now, I should take a little side step here. Did anyone do this in algebra? Determinants. A determinant of a matrix. If you didn't, don't worry about it. I'm just gonna tell you what a determinant is. If you have a matrix where you have A, B, C, D, 4 numbers, the determinant of this is these two numbers multiplied, A times D, minus these two numbers multiplied. I'm going to say BC. So it's like you do this diagonal multiply and then you subtract this diagonal multiply. That's called the determinant of a 2 by 2 matrix. Again, if you haven't seen it, don't worry about it. All right, but we need to do this, okay? So here's what we're gonna do. Our answer, when we do a cross product, our answer is a vector. Okay, dot product answer is a number, cross product answer is a vector. So the answer that we're gonna get is gonna be by first finding the first component. So let's just say that this is our answer down here. Okay, that's our answer. It's gonna have 3 components to it. To figure out what this component is, what we're gonna do is we are going to hide this first column. So we're gonna cover up, I like to put my hand over it or something. I'm just gonna cover up the I column, and I'm going to do this determinant on these numbers right here. Okay, so let's see what we would get. We get -3 times -3 times 3, which is -9. And then I'm going to do what? You know what? Did I put add? Why did I put subtract here? This right here. How many of you have done determinants? Yes?
Determinants, but it's a little fuzzy.
Okay, let me bring something up for you. Let's see here. I want to see if I can find a, let me see images. So determinants can be done on any size matrix, This looks like a good one. Here we go. So this is a 2 by 2 matrix right here. This is what I was showing you, A, B, C, D. Here's a determinant. And then if you do 3 by 3, it gets more complicated. We don't need 3 by 3 yet. We will need it later. So I'll you know what? I'll get into it when we need it. I'll do it. Okay. All right. So let's keep going. I did this times this. That's -9. And now formula is subtract from this these 2 multiplied, which would be -5. All right, any questions on that first part? What would that be, by the way? What's -9 minus -5?
14.
Careful, -5 is +5, right?
The -4.
-4.
-4. Okay, so the first piece is -4. All right, now we move on. We need the second piece. So to get the second piece, here's what we do. Instead of covering up the first column, we cover up the second column. And we do the determinant on these 4 numbers. All right. So let's do that. It's 2 times 3, right? Then minus 5 times 4. Now there's a big catch to this, that I'm about to say here after we get this number. What is that number? 6 take away 20, right? Which is what?
That's -14.
-14. Okay. Does anyone know what I'm about to say? We have to do something to that number. No?
Isn't
gonna
the
be
order specific?
You have to change the sign of that number. When you do the second little determinant, you always use the same formula, but when you get that answer, you change the sign. So even though I got -14, I'm going to change sign. So make sure you put a little note here. You got to change sign. That's going to be +14. Now, when we do the third piece, we're going to cover up the third one and do the determinant on these 4 numbers. And this one, we do not change the sign. Okay, you only change the sign on the middle one. So for this one, I'm going to do, let's see, 2 times -1, that's -2. And then minus, let's see, 4 times -3, that's gonna be -12. So what do we get there? 10? Everyone got that? This is the cross product. If you take those two vectors and you take their cross product, you get this new vector. And this is the computation for it, okay? I think we should run through another one. And then we'll talk about what it means. Yes. Is that your question?
Yeah.
What's the significance of that vector? Okay, good. Let's just do another one. And I might just make one up here. Let me see, unless I have another example. No, okay. So let me do another example here. So why don't we take the vector 2, -1, 5, and let's cross that with the vector -1, -3, 6. All right, so I'm going to try and go a little faster through this. I, J, K. 2, -1, 5, -1, -3, 6. Okay, so my answer is going to be a vector. I'm going to make it real big so I can do all the math in here. Okay, to get the first piece, I cover up the first column. I do the determinant on what's in here. So I'm going to do -1 times 6, that's -6, minus 5 times -3, it's -15. I'll come back and get that answer in a moment. Now, to get the J piece, the part in the middle, I cover up the middle and I do the determinant on these. So 2 times 6 is 12, minus -1 times 5, which is -5. And don't forget, I must change this answer, right? I need to change the sign once I'm done. Then I'm going to do the last piece, cover up the last one. Go here to here, that's -6. Take away, -1 times -1 is +1. And that one I don't change. So my cross product should be, let's see, I think that's 9. Is that 6 take away 15, and 6 plus 15. And then here I would get 7, but I'm going to change the sign. So it's going to be -7. And then I'm going to take this and put together to get -7. All right, you ready? So I'm going to call your name, okay? Let's see, let me do this. I'm going to label this, I'm going to call that vector U, okay, the one we started with. I'm going to call this one V, and then I'm going to call this answer we got W. Well, you know what? Why don't I just not call names? Let me just ask all of you to do this. Just working on your own. I'd like everyone right now to figure out what's U dot W. And then after you figure out what that is, I want you to figure out what V dot W is. Okay, work that out. The dot product from last class. Take this U, dot it with W, then take that V and dot it with W. I'll give you, you shouldn't need more than four minutes to do that.
Sorry, I see, is that correct? The -1 times 5 12 minus -5, isn't that what it's supposed to be?
Where, this one?
Yeah, I think it's
Oh,
17.
did I miss -5? Oh, I did miss
Yeah.
-5. Why are y'all waiting so long to tell me?
Sorry about that.
No, I'm glad you caught it. Hold on. This right here, we're talking about this. It's when we covered up the middle one, it was 12, and then I'm supposed to take away -5. I may have said it, but not wrote it. Okay, that does change things significantly because that's going to be what now? It would have been 17, right? But now it's
Yes.
going to be -17. Yay or nay? We good? Okay.
Yes, sir.
Now go try and do that. U dot W, W dot, or V dot W. I'm going to put up the poll, and when you're done, click yes. Okay. When you've done them both. And when you finish, think about what this means, okay? Think about what your answer means. Okay, I think that's enough time. Most of you got it finished with it. So I'm going to ask Jorge because he asked me earlier. So Jorge, what did you get when you did those?
I got 0 for both.
For both. Okay, what does that mean?
That it's an orthogonal vector.
Mm-hmm.
I just don't know to which vector or if it's both.
It's both. It's both. So this vector that we've created is a vector that's orthogonal to both of the original vectors. So now in a classroom, this is much easier to do. So I'm going to try it with these markers. I know, you might want to, you know what, maybe what I can do is make my screen, not share my screen. That might be easier. And then maybe you can see me better. Can you all see me better or no? So let's say we have two vectors and they're in three-dimensional space and we attach them tail to tail. Okay, there they are. Wherever they are, they are. We have found a vector, a third vector, that is orthogonal to, let's say, the Sharpie pen. So it hits this one at a right angle, but it also hits the black one at a right angle. So it looks like that. You'll see that? It looks like this. Now, it could actually be pointed out the bottom like this, but remember, it's a vector, so it can slide around. But if I attach them all tails together, it creates this. Okay? Now, let me share my screen again. This is the unique and fundamental major property of the cross product. All right. What makes that new vector so special is that it is always orthogonal to both the vectors it was generated from. So we often use the cross product when we are trying to find some vector that's orthogonal to two other vectors. So here's the visualization. See, this visualization is not as, I don't know, Still hard to see. The black one is the cross product of the blue and the red one. It's really tough to see it. I don't think this does a good job of representing it, but if that makes sense to you, that's what we've created. All right. And this will be very, very useful to us. All right. So first thing, show that the cross product of a vector with itself is 0, regardless of the vector. So let's do that. Let's show that if you cross any vector with itself, you get 0. Let's just show it. So let's say I take a vector u, and let's call that vector u1, u2, u3. And now let's take that u and let's cross it with itself. So I'm just going to do I, j, k. I'm going to do u1, u2, u3. I don't know what they are, but it's okay. And let's see if we can go through this cross product fast. So first thing I'm going to do is I'm going to cover up the I, right? I'm trying to cover up the I and then do my little cross product there, or my little determinant on that. So I'm going to do these two together. That's u2 times u3 minus, now I'm going to do these two, and that is also u2 times u3. So that's just 0, right? And then if you do, let's say if we cover up, we can just do one more. I don't think we need to do all of them. But if we cover up the middle one, you see that you'll get u1, u3 minus u1, u3 again. So you get 0 there. And the last one's 0. So wait a minute, let me go back to notes. Did I put 0 vector? Yes, I did. If you cross a vector with itself, you get the 0 vector. I think I said 0. You get the 0 vector, okay? All right. Find a vector that is perpendicular to the plane that passes through these 3 points. So you have 3 points given, right? And those 3 points define a plane. So this extends, so it's kind of like if you have, when we say a plane, it's like a sheet of paper sitting in 3-dimensional space. We have 3 points on that plane, right? We have 3 points on that plane. So those 3 points define this plane, right? My question is, can you find me a vector that's perpendicular to this plane? So you can you find me the vector that's perpendicular to this? So does anyone have an idea of how we could do this?
You can just take the cross product from any 2 of those points. Oh, actually, you would have to get the vector.
There you go.
Of the
Yeah, so this ties into when y'all broke into groups last class, right? When we broke into groups, one of the main things to remember was that I gave you 3 points, right? And so if we want to do a vector that's perpendicular, then we're going to need to be starting with 2 vectors, which means we need to maybe get that vector, call it u, and then maybe get that vector right there and call it maybe v, and then we need to go ahead and cross those 2. Understand? So let's just label these points. I'll label this one 1, 4, 6. I'll label this one, doesn't matter how we label because we're in 3-dimensional space. Doesn't matter. Okay, so let's say those are my 3 points. Let's go ahead and figure out what u is. So let me call on somebody because we're at that point where people should know how to do this. So how about Damien? Is Damien here?
Yeah.
Okay, Damien. So can you tell me what the vector u would be? It's the vector going from this point to this point.
So you just subtract them, right?
Okay.
So it would be -3, or yeah,
Yep.
-3,
Yes. Mhm.
1, and then -7.
Good. Okay. So the reason why we did that, and did these minus these is because our vector starts here and ends here. So you always do these, take away these. All right, how about Margie? Can you do the next one for V? Tell me what that vector would be.
Sure. For V, it's going to be the first is 1 minus, so it's 0.
Okay,
And then a negative 5.
okay,
And then it is a negative 5.
okay, good. So those are our two vectors, right?
Mhm.
Those two vectors live on this plane, right? And so what we're trying to find is a vector that's perpendicular to the plane. So why not just find the vector that's perpendicular to both those vectors? So just cross them, right? So now let's do our cross product. And for this, we'll just do it together and we'll do it fast. Okay, so I'm going to do it right here. I'm going to squeeze it in here. I, J, K. Which one do we do first? Do we do U cross V or V cross U? Or does it matter?
I guess in this case it doesn't, because it's just perpendicular.
That's right. So it'll be perpendicular. Now, remember I said when you have your two vectors and you do the cross product, you're either going to get the vector coming out like that or the one going down like this. They're both perpendicular to both. The one you get depends on which vector you cross first. So if we do U cross V, we're going to get a certain vector. We get V cross U, it'll be same size vector, just pointed in the opposite direction. So in other words, U cross V is not equal to V cross U. That is not true. Dot product works that way. Here's what we can say though. U cross V is equal to -1 times V cross U. That's a property, which means that these two vectors, the only difference between them is that they point in opposite directions, okay? So it doesn't matter which one we do here. We're just gonna do, I'll do U first, so I'm gonna do -3, 1, -7. Then I'll do the other one, 0, 0, -5, -5, and then here I go. So I'm gonna do this without hiding things. I'm just gonna use my finger to cover things up. So the first one I should get -5 minus 35. And then next one I should get 15. And it'll be 15 minus 0, but then I need to change the signs of this one. And then the last one should be 15 minus 0, so 15. So you check, see if we all agree. I get -40, -15, 15. Anyone else get that? Yeah, okay, so there it is. That vector is perpendicular to both of those. Well, I should say that is a vector that is perpendicular to that plane with those 3 points. Questions before I move on? All right. So,
Sure, I had a question.
yes,
So if we did the other side of that triangle and we got the perpendicular vector to say the other point where -2, 5, and -1 is that still a correct answer?
Good question. So I think what's being asked here is that, let's say you had done this, say you had done this vector and that vector, something like that instead. You would not get the same vector, but here's what I would tell you you would get. You would get a scalar multiple of it. So it would be pointed in the same direction. It just wouldn't necessarily have the same length. Does that make sense?
Yeah, I believe so.
So let me try and illustrate a different way. I start out with a vector and another vector, and I do their cross product. I'm going to get a vector like this, okay? That's orthogonal to the black one and it's orthogonal to the blue one at the same time. But let's say we would have taken another vector that lies in that plane, like this one right here, that lies in a plane between these, like 3 points. Then if you were to take the blue one and cross it with the purple one, you would get another vector that would be pointed in the same direction as this red one, but it may not be as long as that one. Or it could even be pointed in the opposite direction like that. They will be parallel. I mean, that's the way I could answer you. They would be parallel. If you chose 2 other vectors, crossed them, they would be parallel, guaranteed.
The answer, I mean, would still be correct though, because they would
Oh,
still
yeah.
be perpendicular.
Oh yeah, because parallel just means scalar multiple. So like someone may have gotten, I'm gonna have to bring up, I don't know if I can undo this. Yeah, okay, so see this right here? If you got an answer, if you got the answer 8, 3, -3, that would also be correct because this and these 2 vectors are scalar multiples of one another. Like if I multiply every one of these by 5, what would I get? Or -5, I should say. -5 would give you this, -5 would give you that, -5 would give you that, right?
Right.
So no matter how you do it, if you do it correctly, all of our answers should be scalar multiples of one another. Or in other words, parallel, right?
Okay.
Good question. So we have a theorem, and I'm going to ask you to remember what we did last class. We said that u dot v, from last class, u dot v is equal to magnitude of u times magnitude of v times cosine of the angle between them. That was a very important theorem that you were supposed to have gotten from last class. Look at this theorem, very similar. But it's not the cross product of u and v, it's the magnitude of the cross product. So remember, the cross product gives you a vector, right? This says that if you take the length of that vector, it should be equal to the length of u times the length of v times sine of the angle between the 2 vectors. Okay, so just jot that down. We'll need it, not very often, but we'll need it. We have one major result of this stuff. Okay, and maybe you can figure it out. What if I ask you to take the magnitude of the cross product of 2 vectors and you get an answer that's 0? What can you tell me about those 2 vectors? We know that when you take the dot product of 2 vectors, if it's 0, they're perpendicular, right? But if you take the magnitude of the cross product and get 0, then what do you think that tells you about these 2 vectors?
They're orthogonal or the same.
They're parallel.
They're
Parallel.
both.
So think about this. When is the only time sine is going to be 0? At what angle is sine 0?
0 or pi.
0 or pi, right? So the only way that this whole quantity is going to equal 0 is if the angle between the 2 vectors is either 0 or pi. In both cases, that means they're parallel. And that's what the next major kind of, well, not major, the next result is. This one right here. 2 non-zero vectors, u and v, are parallel if and only if their cross product is 0. So if you ever take cross product 2 vectors and get 0, you can tell me right now that those 2 vectors are parallel. All right. Do y'all know what if and only if? Do y'all know what this is, if and only if? Have y'all seen that before?
I've seen it before. I just forgot what it meant.
A lot of people think that when they read if and only if, that means like really seriously we mean this. Like, you know what I'm saying? Like really, if and only if, you know, it's like, but mathematically it's actually something else. Okay, so I'm going to take a moment to explain it to you, because I know some of you might be interested in logic a little bit. So let me give you a simple example. If Robert lives in Texas, then Robert lives in the United States. Do you agree with that? If
Yes.
Texas, then Robert lives in the United States. Now, does that work the other way around? If Robert lives in the United States, then Robert lives in Texas.
No.
Doesn't work that way, okay? So we can say this, but we can't say this. So we can't reverse the direction and it still be true. Now, how about this statement? If x is 2, then 3x is 6. Is that true? Okay, can I reverse it? If 3x equals 6, then x must be 2. Yes?
Yes.
Since it works in both directions, here's what I can say. X equals 2 if and only if 3x equals 6. So when you write if and only if between two statements, it means it works both ways. It means if x is 2, then that's true, but it also means that if this is true, that's true. And not everything in math works that way. I'll give you one more example. If x equals 2, then x squared equals 4. Is that true? Yeah? Doesn't work the other way around. If x squared equals 4, then x equals 2. Does that work this way?
Oh, no, because it could be -2.
It could be -2 also. You see? So yeah, I mean, it could be, but it's not guaranteed. This is saying if x squared is 4, then x has to be 2. No, it could be -2. So you could not do an if and only if on here. Does that make sense? Here's a crazy one. No, I won't go there. I'm not going to go there. We're not going there. We're going to get back to class. All right, so two non-zero vectors u and v are parallel if and only if the cross product is 0. That means that if they're parallel, then I guarantee you the cross product is going to give you the 0 vector. Also, if the cross product of two vectors is the 0 vector, I promise you they're parallel. It works both ways. So it's a very strong condition to be an if and only if because it works both ways. All right. Area of a parallelogram formed by two vectors. This is a really cool, like we've already talked about, when you take two vectors and cross them, you get this new vector, right? It's perpendicular to both or orthogonal to both. And that's pretty cool already. But this is just mind-blowing. The length of that vector, okay, the length of the cross product is equal to the area of the parallelogram formed by the two vectors. This is crazy stuff right here. So let's say I take, let me get two vectors out here. I don't know why I didn't have these formed before. Okay, so I'll try and do it this way. Oh, I've forgotten how to do this. Stop moving. Okay. Okay, right here. So I have two vectors here. This black one and this red one. Do y'all see those, the black vector and the red vector here? If we create the parallelogram that is formed by both of those vectors, if we look at their parallelogram, then the area of that parallelogram is equivalent to the length of the cross product vector. And that's just mind-blowing, okay? But that's the way it is. So how can we use that? Well, how about this? So this is the way I want you to think about this. We walked into class today. If I would have said to you at the beginning of class, hey, I'm going to give you 3 points in three-dimensional space, 3 arbitrary points. Those 3 points create a triangle, right? If I would have then said, hey, give me the area of that triangle, you would have been like, well, you should have been like, what? How am I going to do that? You know, this triangle is sitting in just arbitrary space and I'm supposed to find the area of it. Like if it's on a flat sheet of paper, we can do it, because flat sheet of paper, you can always find, you know, the base and the height and do some math to it. But this is saying that doesn't matter, right? Draw me this triangle, 3-dimensional space. Boom, here it is, sitting in 3-dimensional space. The area of this is what we want. But if we take 2 vectors, so let's create vectors here to here, there's a vector. And then let's create another vector that goes from here, let's say to here. Those 2 vectors form a parallelogram. And I can tell you that the area of the whole parallelogram is just the magnitude of the cross product of those 2 vectors. That's what the previous note said. Take this vector u, take this vector v, cross them, take the magnitude, that gives you the area of the whole thing. So all we need to do is do this and then take half of it. And that'll give us this triangle, right? All right. I think what I'm going to do is I'm going to leave that to you. So what I'd like for you to do is we're going to do a practice here, because I know we have stuff coming up. I'm going to go into my email right now. I'm going to send everybody a Dropbox link. Okay. This is going to be a bonus problem for you to just finish this problem out, but start it from scratch. Okay. You have to go create your vectors. You have to cross them, find the magnitude, do all that. And I want you to submit it to me, but here's the catch. The Dropbox link that I send in the email, I want you to submit your work to me. And when you submit your work, I want you to submit more than 1 page. So your first page, just make this like your cover page and just put like your name or whatever. And on your second page, have your work. And the goal for you is to somehow turn both of those documents into one PDF document, a single PDF. So you might have to use a scanner or use your phone. You can take pictures of your work, condense it down. We're practicing for you submitting work to me later. Does anyone have a question on what I'm asking for? All right, let's make this bonus problem. Oh, go ahead.
You said the screen we're seeing right now, that's going to be the cover page, and then the work separately and put it into one file as a PDF, right?
Yeah, well, it doesn't matter what, I just want you to submit more than 1 page. So I want you to prove to me that you can actually take multiple pages and turn them into one file. So I don't care what's on your pages, just as long as it's more than 1 page.
Okay, I understand.
And as far as the Dropbox link, you know what? Let me just make the Dropbox link and I'll throw it into the chat for you. You can just grab it right now. So I'm going to call this 2415 bonus from today, 127. And actually work the problem out. I want to know the area of that triangle, okay? Okay, so in the chat, coming to you now. Done. There you go.
Can you send it through the Canvas email too?
No, I want you to try using that Dropbox link.
Okay.
Oh, you mean, will I send the link? Is that what you're saying?
Yeah, through Canvas.
Yeah,
email?
I'll send it. I'll send it through the Canvas also.
All right.
Are there any questions? I think we're going to call it a day here at this point, and I'll let you, take the rest of the time to go mess with that problem. Oops, wrong page. And we're a little bit ahead, so I'm not worried about it right now. But that's it. You're free to go once you've got that link, and I'll hang out for a minute if you have a question about anything.
Can you bring the problem back up again?
Yes, I will. Hold on. Let me just get this sent to everyone.
Yes, sir. Have a good day.
You too. On this email, I'm just going to call it "huh" because people aren't going to know what it. Anyone who wasn't here today isn't going to know what the hell I'm talking about, and that's okay with me. So there you go.
Sir, I might have missed it, but did you say when it's due, or is it just whenever?
No, I didn't say when it's due, but let's just try and get it done, you know, by the time we start class again. So Monday, you know,
Okay.
I'm not in any hurry for it. It's really just a practice, because I don't want the mini exams coming to me as like 15 pages, 15 different files. I want one file. Okay, I'm trying to bring this problem back up. There we go. If you look at this problem, I'm using the same points that I've been using throughout the entire, like these are the same points from the problems before. So like you've already created vectors for these, right?
Oh,
Aren't these the same points? Aren't these the same points from when I broke y'all out into groups the other day?
Yeah, I was gonna say that.
Yeah, I mean, it's really just this, it's work you've already done. You just got to do a cross product and take a magnitude. And then take half of it, don't forget, because this is the triangle, not the whole parallelogram.
These are the same points as example 4 also.
Yep.
Great.
Yeah, it's really just to cut down on having to do the same thing over and over and over.
So I have a question. It doesn't matter which two of the points we pick here, as long as we just take the cross product, the magnitude, and divide by 2.
Mm-hmm. That's right. It's all amazingly going to work out the same. The lengths of all those vectors will always be the same no matter what. The vectors won't be the same. So like if two people pick certain vectors, right? Like if one person picks those two, let's say these are our 3 points. So if one person picks that and those two vectors, their cross product vector is going to be different than your cross product vector if you pick, like say this one and this one. But what I can guarantee is that the length of those vectors will be the same. Okay. Which is kind of amazing, but that's the way it works.
And you said you wanted a cover page, right?
Well, I just want multiple pages. So if you
Okay.
if you do all your work on one page, then you're only going to submit one page to me. I don't want that. I want you to submit multiple pages. So
Right.
you just
Yeah,
put
I
a
get
cover
you,
page
but
on it or something. Or
just
draw me
whatever
a-
on the cover page, or
What's that?
just whatever on the cover page?
Yeah, just draw me a picture or something. I don't know. I don't
Okay.
care as long as it's 2 pages.
All right.
Just put your name, whatever. All right. Anything else?
I don't have anything else. Have a nice day, sir.
You too. Everyone have a good week.